I want to talk for today and tomorrow about one last sort of graph theory construction, one more graph theory concept. And it is vaguely similar to Euler circuits and Hamilton circuits in that it's another way of sort of covering the whole graph, but it's different. It's not circuits. Anyway, it's called the spanning tree. Spanning tree. The spanning tree of a graph. Trees, I guess. I mean, they're typical, homework question about this. I show you a graph and I say, find me a spanning tree for this graph. So it's sort of vaguely like finding an Euler circuit or a Hamilton circuit, but it's not a circuit, and it's different. But you'll see the techniques for finding spanning trees are very much similar to the Hamilton circuit stuff, especially. Anyway, let's talk briefly about first of all, what a tree is. A tree is this is a technical graph theory term. A tree is a graph with no loops in it. So, for example, here is an example of a tree. It would be a graph which has, of course, vertices and edges, but those vertices and edges never make loops. So this is a tree. It looks like sort of by itself, it looks like kind of a branching pathway, and it's all branches. That's why it's called a tree. No loops. Only branching of the edges. No loops. That's the point which makes it a tree. I should say a tree is a connected graph. I should have said that. Squeeze it in there. A connected graph with no loops in it. Actually, there's a word for this. I think is kind of silly, but the word that's used in graph theory for a disconnected graph with no loops would be, something like this, together with maybe one of those. A disconnected graph with no loops would look like that. It's like a bunch of trees just kind of next to each other. That's called a forest. Isn't that cute? Because it has several trees. I don't make the rules here. Anyway, a connected graph with no loops in it, that's a tree. So something that would be, not a tree would be a graph which does have some loops in it. Something like this, maybe. This looks kind of tree-like, but it's not. So this one here is not a tree, and the reason it's not is because of this little part there, which made a loop. All right, that is not allowed in a tree. So the one on the left, it is a tree. The one on the right is not a tree. All right. So if I give you a graph, to find a spanning tree, it means you find a tree inside that graph which touches all the vertices. So inside a graph, a tree touching all the vertices. A tree touching each vertex is called a spanning tree. That's what we're going to talk about today and tomorrow. A spanning tree. All right, for example, if I just draw sort of a big grid and make this into a graph, this is like a 4x4 grid. All the crossings are vertices. What would a spanning tree look like? There are many spanning trees, but it's a tree inside that graph which touches all of the vertices. So I'm going to just like I would for a Hamilton circuit, I'm just going to scribble in edges. Like I said, there are many, many ways that you could do this, but I'm going to scribble in a bunch of edges in such a way that it's a tree and it touches all of the edges. If you're doing this on your paper, you don't have to do the same way I did. It just has to be a tree did I just say which touches all the edges? It touches all the vertices. That's what's important about a spanning tree. And I think I'm done drawing. What I scribbled in there is a tree because the red scribbled edges have no loops in them. So that is a tree, and it's a spanning tree because it touches all the vertices in the graph. All right, that's called a spanning tree. Here's another example. How about this graph here? Can you make a spanning tree on that graph? Yes. I mean, it's not hard to find just any old spanning tree. There are so many ways you could do this. You just scribble in some of the edges in a way which reaches every vertex but has no loops in it. All right? That is a spanning tree of that graph. Yeah?
So you can have like 3 of the scribbled edges touching the same.
Yes. Yes. So, I mean, it's kind of like a Hamilton circuit in that it touches every vertex, but it also is allowed to have several edges meeting. In fact, that's almost always going to be necessary for a spanning tree. I'm trying to think. I think really it is always necessary, unless your graph is just like a single edge or something like that. All right. This is a spanning tree. Okay, let's think about, first of all, why would you want to care about spanning trees? You know, Euler Circuit is like, that comes up for, say, Mr. Plow, or if you have a graph and you want to use up each edge in the graph in a circuit, that's when an Euler Circuit is important. A Hamilton circuit in the real world is maybe more, comes up more often. That's when you have to visit each one of a bunch of locations, but it doesn't matter which edges you use. A spanning tree, this is used, so these come up in the real world when we're doing something like connecting things together, like with like electrical wires or pipes or something like that. You know, if you have a bunch of houses in a neighborhood and you want to lay down water pipes for them all, those pipes will end up making a spanning tree. They go to all the houses, but you don't want water pipes to have a loop in them because that's not how water pipes work, right? The water's supposed to flow in one direction. There are no loops in pipes. And the same is true for electricity for the most part. You don't want loops made of electrical wires. Like all the wiring in your house is a bunch of wires that go to all the different outlets, but they are arranged in a tree format. There are no loops in those wires, or else your house would burn down or something. Do you ever take an extension cord and like plug the one end into the other end, and you feel like you're somehow like living dangerously? It's not actually dangerous if it's just one extension cord. But if you somehow had this one in 2 ends, and then you also connected a third one to it that was plugged into the wall, that might be dangerous. I don't actually know. Don't try that. Anyway, spanning trees, they come up when you need to connect things to, you need to connect a bunch of stuff together, but in some situations, it is inappropriate to connect things together using loops, for instance, water pipes or whatever. All right, I'm going to draw just a couple more examples, and then we'll talk about how to actually find spanning trees. So here's another simple example using, say, things laid out in a grid. The other one I just sort of made up at random, although if you were really trying to, say, wire up houses for electricity or something, you would do it in some kind of systematic way. I think it would make sense in a situation like this. If you could imagine these are like city blocks, you might run your wires sort of like this. You have them going down one main street and then across the other streets like that, maybe. That would be a sensible way to wire up a grid in this configuration. It would not be sensible to do something like, I'm drawing the same graph here. How about if I did this? Wouldn't that be even cuter? Actually, that second one there is not a spanning tree. So this is a spanning tree. This one is not a spanning tree. What's wrong with that second one there? Yes, somebody gave an insightful one-word answer. Loop. Yeah, it has loops in that second one there. For instance, you can see a loop right here, or you can go all the way around the outer edge. You don't want that in a spanning tree. All right. Just to clarify or make very obvious, there have been in the past few weeks, we've been talking about. You could summarize in terms of like 3 different types of. Here's a graph, you find me something or other. All right, we started with Euler circuits. I just wanted to show one picture of these things kind of all next to each other. Then we talked about Hamilton circuits. And then right now we're talking about spanning tree. I'm going to draw the same graph 3 times and then see if we can draw sort of one of each. You may, from time to time, find yourself wondering, isn't that the same as a Hamilton circuit or something like that? They're not the same. They are vaguely similar, and the ways in which you think about Hamilton circuits and spanning trees are pretty similar, actually, but they're not the same kind of a thing. So I'm drawing the same graph 3 times. And this is nice sort of in the context of reviewing for the final exam. I could give you the same graph 3 times and say, find me this, find me this, find me this, right? The Euler circuit is quite different. An Euler circuit, let's say I'll choose this point down here. I hope you remember how to do this. The Euler circuit is one which uses every edge once without repeating any edges. So I'm going to try and draw my Euler circuit in a way that is sensible. And they can be a little tricky to find sometimes, but I'm a professional. Something like this, right? I hope you remember how to do this. If not, you may want to refresh your memory before the final exam. That's an Euler circuit. I use every edge once without repeating any edges, all right? A Hamilton circuit is a circuit which touches every vertex once without repeating any vertices. So, and I remember how to make Hamilton circuits is a little less straightforward, and it involves some amount of tricky reasoning, but I'm going to start by scribbling in all the edges which touch degree 2 vertices, which would get me all of those, and then I would exclude the edges which makes subcircuits and whatever else. Actually, I don't want to complicate this picture too much. Can I just draw in what I would have to do? How about this? There's actually several different Hamilton circuits in that second one, but that which I just drew is one example of a Hamilton circuit in that second one. I failed to use many of the edges, but that's part of what a Hamilton circuit is. You don't have to use all the edges, you just have to touch all the vertices in a big circuit. And the spanning tree is you have to touch all the vertices, but without using any loops. And this is actually quite a bit easier. You can more or less choose whatever you like, as long as you don't make any loops. So maybe I'll come over here. I'll also use this guy there, this, and how about that? That's a spanning tree. And there are many other spanning trees. And it's if I just give you a random graph, sometimes it can be hard to find a Hamilton circuit. It's basically always easy to find a spanning tree. You just pick whatever edges you like. Just make sure you don't make a loop, and make sure you meet all the vertices. All right. So the question of, and let me just point out, this is something that somebody asked a moment ago. A spanning tree has no circuits in it. Has no loops in it, but it may, and in fact, in most cases, it must have 3 edges meeting at a vertex. I will say 3 or more. Oops. It may have 3 or more edges meet at a vertex. This is not allowed in a Hamilton circuit, but it is allowed in a spanning tree, and in fact, it almost always has to happen in a spanning tree. It may have 3 or more edges meeting at a vertex. All right. And it is a fact that every connected graph has a spanning tree. This is not true of like Hamilton circuits. There are some graphs which don't have a Hamilton circuit, as you saw in the homework and the quiz. Or not on the quiz. The one on the quiz did have a Hamilton circuit. But anyway, every connected graph has a spanning tree, and they're easy to find. So there's not really much to talk about in the sense of like methods for finding spanning trees. You just basically can make it up as you go along, and you will find a spanning tree, no problem. What is interesting to talk about, and this is what I want to spend our time today and tomorrow talking about, every connected graph has a spanning tree, but it's interesting to find the best spanning tree, the best one, in a weighted graph. Remember, a weighted graph is a graph where the edges all have numbers on them representing distances or costs or whatever, and you want to minimize the total weights. This is what we do in the Hamilton or the traveling salesman problem. And you can ask a similar question about spanning trees. If I show you a graph with weights on it, can you find me the spanning tree with smallest total weight? This is what I want to talk about for the remainder of our precious time together. Here's an example. This is sort of a made-up real-world example here. Let's say I have 6 different things. Maybe these are like light-up lawn ornaments. I don't actually have light-up lawn ornaments, but maybe some inflatable baby Yodas or something like that outside. And here's the outlet, and I want to wire them up using the smallest total amount of wire because I don't want to spend a lot of money on the wire. So how can we wire them up? My light-up gnomes. Wire them up using the minimal amount of total wire. And I would, to make it specific, I'll tell you the distances between these things. Let's say these are distances in feet or something. That one is 8, that one is 13. Across the bottom here is 20. Say this is 7 and this is 12. Like that. All right? Those edges there are places where I might put a wire, but your job is to determine where should I actually put the wires so that they are all connected to the outlet, but there are no loops in the wiring, right? Because obviously you don't want loops in your electrical wiring. Wire them up using the minimal amount of total wire. So this amounts to finding what we're doing here in this problem. We're finding a spanning tree which has to touch the outlet on one of its points, but that really doesn't matter. I mean, it has to touch everything here, and there's nothing special about the outlet, really. In the real world, there is something special about the outlet, but when it comes to wiring them up, there's nothing. The outlet is just one of the points that needs to be connected. We're finding a spanning tree with minimum total weight. And this is called this is not a fancy term here, the minimum spanning tree. And I'm going to write MST, the minimum spanning tree. And this is a big deal in the real world in many situations. if you're actually doing electrical wiring or pipes or something like that. But it's also, this is very important when it comes to wiring and routing of computer networks. Just like other kinds of water pipes or something, internet connections tend to be sort of one way. You don't really want information to be flowing around in loops. That doesn't really make any sense. That's not the point of how the internet is supposed to work. So this business about finding minimum spanning trees are important. You want it to be the minimum in the case of the internet because you want to choose like the least amount of wiring that is necessary to make all the connections that you want to make. Because it's faster that way and cheaper and everything like that. All right, how do you find the minimum spanning tree? That's what I want to talk about. And this actually turns out to be a lot easier than finding minimum Hamilton circuits. That requires, if you want the actual answer, you have to use the brute force, which takes forever. Finding the minimum spanning tree is actually much easier. Lucky for us, because it is such an important problem in the real world, is much easier than finding minimal Hamilton circuits, which is what the traveling salesman problem is about. And we're going to talk, there are many techniques for doing this that people use all the time in the real world. I just want to talk about two of them. These are two methods, and we'll do one today and one tomorrow, because I don't think we can squeeze them both in today. Two methods for finding the minimal spanning tree in a graph. So on our final exam, you should expect me to put a graph, maybe like this one right here, and say, find me the minimal spanning tree using this or that procedure. There's two of them, and they both, unfortunately, they are named after people, which makes it hard to remember. But the first one is called, although I do like the names of both of these people, Kruskal's algorithm is the first one. I know essentially nothing about these two people. Kruskal's algorithm was invented by Kruskal in the 1950s. And this actually, I'm going to try not to refer to this as Kruskal's algorithm too much, just because that's not very descriptive of what it is and how you do it. But it's almost exactly the same as the sorted edges algorithm, which we do know about. That's on the homework for tomorrow. The sorted edges procedure for finding Hamilton circuits. You can do that same thing to find a spanning tree, and it's almost exactly the same as the sorted edges. That's called Kruskal's algorithm. And then the other one, which we'll talk about next time, is Prim's algorithm. I like this one too. I like the name of it, I suppose I like the algorithm too. Prim's algorithm. And this one is just like the nearest neighbor. So I'm going to refer to them by those other names just because they're more descriptive. And it can be hard to remember which is which. Nearest neighbor. All right? Two different ways of solving the same problem. Kruskal's algorithm and Prim's algorithm. They are analogous to the sorted edges and the nearest neighbor. So let's just talk about Kruskal today. I'm going to refer to this as sorted edges for minimum spanning trees. All right? This is more commonly known as Kruskal's algorithm, but just so that we can all keep it straight, I have a hard time remembering which is which. I'm going to call this one the sorted edges procedure for the minimum spanning tree. I hope you remember how to do the sorted edges. It's what we did in class on Friday. The sorted edges involves writing down all the weights in order from lowest to highest, and then choosing those edges sort of one at a time. So what we're going to do is consider all the weights. You can either write down a list of them or just sort of try to look at the graph and hold them all in your head at once. Consider all the weights from smallest to largest. And we're going to choose one edge at a time to add into the spanning tree. This is exactly like you do the sorted edges for a Hamilton circuit. Choose edges one at a time to add into the tree. and you go cheapest, or I'll just say least weight to greatest weight. Right? You start by adding the lower weight ones. Come on now. Greatest weight. All right? Now, in the sorted edges for a Hamilton circuit, there are two rules. The rules are you may never make a subcircuit, and you also may never have three edges which meet at a point. When you're doing a spanning tree, you are allowed to have three edges at a point. You are not allowed to have a subcircuit. So choose edges one at a time to add into the tree from the least weight to greatest weight, and never pick an edge which makes a loop. This was one of the rules in the sorted edges procedure for Hamilton circuits. In that one, you also don't allow three to meet at a point, but for the minimum spanning tree, you do allow three to meet at a point. That's okay, all right? And I'll just say stop when it's done, when it's a spanning tree, which remember means it touches every vertex. With no loops. All right? I want to see if we can do this with that example that I drew before. Maybe you still have it on your paper. If not, you can copy it down again. Here is that example. I have another example to do, which I actually printed out, and I'm going to hand out. All right, let's try to do the sorted edges procedure right here. This is the same graph that I drew before. What I said, consider all the edges from cheapest to most expensive. So I'm going to try and write down a list of all the weights here. There's 2 4s, a 5, a 6, a 7, a 8. There's no 9. There's a 10, 12, 13, and 20. All right, I think I got them all. And I'm just going to choose to include these edges one at a time, starting with the cheapest one. So start with the 4s, and I'm going to take both of those 4s. All right, I use these two. Next is the 5. Can I use the 5? You look over here. Remember, the rule is you cannot make a loop, but you can have as many. You can have 3 meeting at the same vertex. So in this case, I can use the 5. So I'm going to do it. I can use the 5, right? Can I use the 6? What do you say? I see them shaking their heads. You cannot use the 6 because that would make a loop. So no 6. X out the 6. Can I use the 7? I think I can use the 7. The 7 does not make a loop, so scribble it in. All right. Can I use, I took the 7. Can I use the 8? No, the 8 makes a loop with those 2 4s, so cannot use the 8. Next is the 10. What do you say? Can I use the 10? Nope, they're still shaking their heads. The 10 would make a loop right here, this sort of big loop, right? And so the 10 is illegal. No 10. The 12, I believe the 12 is legal. It does not make a loop if I take the 12. And actually, after taking the 12, I think I'm done now, because the scribbled edges now meet every vertex. So this is a spanning tree. All right, I took the 12. If you go too far, you just won't get any more. If you should, even if you kept going, you should consider the 13, but that makes a loop here, so the 13 is not allowed. And then consider the 20, but that makes a loop here, so the 20 is not allowed. So this is my final answer. I suppose the shape of it looks like this. Like a little Blair Witch thing. Is that what that thing looked like? I don't know. That was a long time ago. I never saw that movie, actually. I remember that little thing. All right. Great. This is how you find a spanning tree using the sorted edges. One great thing about this is, if you do it right, actually, this is guaranteed to be the best spanning tree. If you recall, when we talked about Hamilton circuits, using the sorted edges doesn't necessarily get you the best answer. It gets an answer which is probably pretty good, but doesn't always give you the best answer. In terms of spanning trees, the strategy works much better, and the sorted edges procedure always is guaranteed to give you the best spanning tree. So it's really, this version of the sorted edges, you might say, is better than the other one, because this one actually is guaranteed to solve its problem in a way. The Hamilton circuit one gives you something which is probably a good answer, but not necessarily the best answer. All right, what I want to do in conclusion, we're probably not going to stay the whole time today, but I want to try this big graph on the paper. If you do it right, it'll only take you a few moments. Please save this paper for next time, because we're going to do Prim's algorithm next time, and I want to use the same example here. I'll bring some more in case you get a question. Bring it if you can. You'll see 2 graphs on each side of the page, but they're all the same, just in case you mess it up. Everybody got one? So your job is to do the sorted edges procedure here to find a minimum spanning tree. I'll give you a moment, then I'll come around and see how you're doing. If you know what's up, these are not difficult, and actually, if you know what you're doing, it'll only take you a moment to figure it out. I hope the labels are clear. Now you can start by writing down a list of all the numbers, or you can just kind of try to look at them all and pick out the smallest one in each step, which is what you want to do. All right, can we talk about these? I saw most people doing great. I hope you are doing great. consider, I tried to write down all of the weights. I hope that I didn't miss any. You can just, you can do this without writing them down by just looking on the picture and seeing where's the smallest one overall. It's the 14. That's where I should begin. So I begin by taking the 14 here. I'm going to try and sort of highlight them. Actually, I think I have a highlighter. I never used my highlighter on here. Yeah, look at that. Can you see that all right? It's a little faint. Do I got options? No. I'm going to scribble it instead. The big line. All right. So I picked that one first. That's the cheapest overall. And then the next one would be 15, which I can take without making any loops. You just add them in as long as they don't make any loops. The next one, so I took the 14, the 15. The next one is 16, does not make a loop, so I take it. The next one is 18. The 18 does make a loop here, so you cannot use the 18. The 19 is next, which looks good to me. The 20 is next, which I can use right here. If you did this, you should have got exactly the same as I did, right? Now, when there are sort of ties with the numbers, it's possible to get two different correct answers, although for this particular example, that never happens. Next is 22, which is going to make a loop, so I don't take the 22. Next is 30, which is here, which I can include. And there's another 30 over here, which I will include, all right? Is anyone concerned that this 30 over here isn't even touching the rest of the stuff? Oh, everybody has questions.
I forgot to record.
I left out. Oh, that means I should not have taken this 30. All right. I know when everyone has questions at the same time, it's a bad sign. Yeah, I forgot. There's a 24 in there. Sorry. 24. I hope that you didn't do that. So I should have taken the 24. That means I cannot use that other 30, but I can use the big 30 over there. Yeah.
Real quick, you just want us to express our final answer as the spanning tree?
Yeah, just draw a picture of it.
Right.
It's not, with the Hamilton circuits, you could write it down with the letters or something, but there's no real convenient way to do that in a problem like this. You just draw the picture of it. All right, any more complaints? No. Thank you for your complaints. By the way, do the course evaluation survey. If you want to complain some more, that's the place for it. Okay, I used the 30, but not the other 30, right? Next would be 31. That is okay because it doesn't make a loop. And the other 31 also fits in nicely. Next is 36. Over here, that's not allowed because it makes a loop. 38 is here. That makes a loop, not allowed. 39 is here. That also makes a loop. 43 is here. That also makes a loop here. 49 also makes a loop. 50 is here. That one is allowed. And I think now I'm done. All right? You're done when your tree actually touches every vertex of the graph.